Now that you have completed the guided inquiry on the mole, we will supplement that information by providing additional information which will reinforce the understanding and definition of the mole. We will also conduct mathematical conversions between moles, mass, and particles and atoms. And this calculation is very important to chemists because I'm always concerned about having the right amount of reactants that would of course yield me the right amount of products. The mole is nothing really but a big number. The extreme smallness of atoms requires us using a very large standard sample, a mole. In other words, it requires us using a very large number so that we can mass grams of atoms in the lab. The idea was proposed in 1811 by Avogadro, who was a physicist, but it wasn't accepted until about 50 years later. The official definition of mole is simply this: it is equal to the number of carbon-12 nuclides whose mass is equal to 12.0000 grams by definition. So if we take that mass of carbon-12 nuclides and essentially divide it by the mass of one carbon nuclide, we get Avogadro's number. And as you already know, we round it off to 6.022 times 10 to the 23rd. Another thing you could say about the mole is simply this: it's just a large number with a name to it, just like a dozen. A dozen is the name of 12, and you could have 12 anything, 12 eggs, okay, 12 cars, 12 whatever. A ream of paper is another name for a number. A ream of paper represents 500 sheets. So in the same way, a mole of atoms, cars, elephants, whatever, is nothing but 6.0222 times 10 to the 23rd items per 1 mole. Also, we could say that the units of Avogadro's number are 1 over mole or mole inverse. Just to give you an idea how big this number is, if you had a mole of marbles, it was spread over the earth, and it would result in a layer which is 3 miles thick. Also, if you had a mole of dollars, you would be able to provide each of 6 billion people, which is somewhat less now of the world population, a $3 million income per second per 100 years. So if you had ever asked me, would you like to be on that show that is called the what is this? It's called the Do You Want to Be a Millionaire? I would say no. I want to be on the show that asks me the question, do you want to be a millionaire? Also, if you had a mole of sand, you would be able to cover the entire state of Texas with a 50 feet thick layer. Also, more importantly to us, if I have a mole of atoms, and as you can see here in this picture, I have copper at the top, and going clockwise I have aluminum, iron, sulfur, iodine, and in the center I have mercury. Well, 1 mole of any atom or compound contains, of course, the same number of particles, but please notice that 1 mole of any of these elements that you find here weighs not the same. As you can see, aluminum weighs 26.98 grams, 1 mole of that, but 1 mole of mercury weighs 200.6. So this is an important concept that you have to always keep in mind. The 1 mole only indicates that when I'm comparing compound to compound, atom to atom, that when I say I have 1 mole, I'm saying that I have the same number of particles, but I'm not saying that I have the same number of mass. So now we can start converting masses to moles, particles, atoms. And in order to do that, we are required to use dimensional analysis. In order to use dimensional analysis, we need to define, first of all, mathematical relationships. We have to devise conversion factors, and then we need to apply the correct conversion factor or factors to get the answer with the desired units. Once we know the units work out, then we do the math. First, let's talk about some typical relationships that occur in chemistry. As you can see at the very top of this picture, if I have one molecule of methane, I have, of course, one carbon atom and 4 hydrogen atom. This would be my mathematical relationship. Of course, if I have 10 molecules of methane, I have a corresponding number of 10 carbon atoms and 40 hydrogen atoms. And if I have 1 mole of methane molecules, I have Avogadro's number worth of methane molecules, but I would also have 1 mole of carbon atoms and 4 moles of hydrogen atoms. How do we use these relationships? Here are some commonly used ones. That 1 mole of anything is equivalent to the molar mass of that anything in grams. Meaning, if I have 1 mole of methane, I must have 6.04 grams of methane. In other words, the molar mass of methane. Another commonly used relationship is 1 mole, of which of course you know this already, is equal to 6.022 times 10 to the 23rd particles. And by the way, I say particles to mean molecules, formula units, or atoms or ions. 1 mole of methane, in this case, would be equal to 6.022 times 10 to the 23rd molecules of methane. If instead I compare molecules to atoms, then one single molecule, will contain a certain number of atoms as described by the formula. So 1 molecule of methane has 5 atoms. Or I could also say that 1 molecule of anything would correspond to a specific number of specific atoms in the formula, such as 1 molecule of methane contains 4 atoms of hydrogen. So now, what do I do with this information? Well, I'm able with that information to create conversion factors that I use in my dimensional analysis calculations. So I could say 1 mole of methane is equivalent to 16.04 grams of methane. I'm looking now at the right of that first line that we have up there. Or I could also create the conversion factor, which is the reverse. 16.04 grams of methane is equivalent to 1 mole of methane. Now I can do the same for the other relationships, as you can see here. How do we use this mathematical relationships and conversion factors? Well, in converting mass to moles and particles and atoms, there is a specific sequence, as you can see in the box at the top of this table. One goes from mass to moles to particles to atoms, and of course one can go the other way from atoms, particles to moles to mass. And here's what's involved in doing this kind of conversions. Well, in going from mass to moles, we use the fact that 1 mole is equal to the molar mass of that specific substance. And we would use the conversion factor on the left if I'm trying to go from mass in grams to moles. Of course, I would use the other conversion factor, the one on the right, if I'm trying to go from moles to mass. This, of course, will become obvious as we do some of the calculations. What is involved in going from moles to particles and back? Well, Avogadro's number. As you know, Avogadro's number is equivalent to 1 mole. So I would use either one of those two conversion factor, depending which way I'm trying to go. Am I trying to convert moles to particles? Well, then I will use the conversion factor on the left. Am I trying to convert particles to moles? Then I would use the conversion factor on the right. And the same process, of course, occurs in going from particles to atoms, except that in going from particles to atoms, we use the formula subscripts. And how do we use them? Well, we can say that a certain number of atoms is equal to 1 particle, let's say 1 molecule, and vice versa. and use the appropriate conversion factor. Let's apply what we learned. Let's convert mass to moles. How many moles are there in 13.3 grams of methane? Well, if you look back at the sequence that one has to follow in order to do these conversions, you will realize that you need the molar mass of methane, which you can calculate directly from the periodic table. And you would realize that you are going, of course, from mass to moles, and in doing so, therefore, you would start writing the amount of mass of methane, and then you would create the conversion factor that appropriately gives you moles. So how would you do that? Well, you would put, of course, the molar mass of methane on the bottom and the 1 mole of methane on the top. And as you can see, the units of grams of methane cancel out. And what am I left with? Well, I'm left with the desired units, moles of methane. Now I can do the math. And that is my answer. Well, let's go from moles to mass. How many grams do 0.234 moles of methane represent? Of course, you already know the molar mass of methane, and at this point I ask you to stop the presentation, calculate the grams that these moles represent, and then restart the presentation to see if your answer matches the answer that I'm going to show you. So please stop the presentation now. Welcome back. I'm sure you figured this out very quickly. Of course, we start with the value that is given, 0.234 moles of methane, and now we construct a conversion factor that puts moles on the bottom, meaning 1 mole of methane, and the equivalent molar mass of methane on the top. The mole units of methane cancel out. I'm left with the desired units, and here is my answer. Okay, let's move on. Here are some guidelines that I recommend you follow when doing dimensional analysis. Right now, dimensional analysis for these calculations is somewhat simple, but later it will become more difficult and it's easy to get confused. So start this good habits now. First, you identify useful equalities, true useful equalities. They have to be equalities, mathematical relationships that are true. Then you set up a string of conversion factors that lead to the answer with the desired units. How would you do that? Of course, you would write values with full units. Please do not write just grams or, as in I'll show you here, just methane. When you cancel out the units, line out the complete unit, not just part of it. When you use molar masses, it's recommended that you use a value of molar mass that is 1 sig fig more than required by the problem, since that'll give you the most accurate answer, or the most precise answer, I should say. Next, do the math. In other words, once you work the units out, you're almost assured, let's say 90% sure, that you set up the right series of conversions. So now you do the math. Multiply by anything that is in the numerator and divide by anything that is in the denominator. And there is one trap here. There's a tendency, if you have more than one denominator, is to divide by the first one and then multiply by the others. So let's see if you can do this problem. How many molecules do 4.60 grams of, hope you know how to name this compound, tetraphosphorus decoxide represent? See if you can do it. Please stop the presentation now. Welcome back. You should have realized that here's a sequence: mass to moles to molecules. And in order to do that, you will start, of course, with the amount given. You will convert that to moles. Of course, you have to figure out the molar mass of the compound. But as you can see at this point, we are at moles. But the problem wants molecules, so I have to do one more conversion. I have to relate 1 mole of the compound to Avogadro's number worth of molecules. As you can see now, the moles cancel out, and what am I left with? The desired units, the molecules of tetraphosphorus dicoxide. Now I do the math, and that's easy. Here's the answer: 9.76 times 10 to the 21st molecules of tetraphosphorus dicoxide. Let's go on. How many phosphorus atoms are found in 4.60 grams of tetraphosphorus dicoxide? Stop the presentation now, work out the answer, and see how it compares with what I have calculated here. Welcome back. Let's see how well you have done. Here is the sequence, and here is the series of calculations. Once again, we start with the value given. We then convert that to moles. We convert the moles to molecules, and now we have one more step, right? We have to convert the molecules to phosphorus atoms. How many phosphorus atoms are in one molecule? Well, for every one molecule of the compound, I have 4. Do the units work out? Yes, because my answer now will give me phosphorus atoms. Now I can do the math, and again, that's fairly easy. And here's the answer: 3.90 times 10 to the 22nd phosphorus atoms. We come to the end of our presentation. Please review it as needed, and then proceed to the next one.